All right, welcome everybody to another stream where we will be doing some more Rust today. I hope everybody is doing well. I was just talking to the chat and letting them know that it's quite hot here. So for anybody watching in the future or in another hemisphere where it is not this hot, yeah, I hope you're doing better than I am right now. But today's going to be an exciting one, hopefully, but not too long. What we're going to be doing is we're going to be working on Rust iterators and learning how iterators work, what iterators are, implementing some of our favorite iterators from the standard library, and making sure that we understand what's going on and kind of the traits that and structs and different types that work together well with iterators. The ultimate goal that I'd like today also is I have seen some comments out there that iterator collect, so the dot collect method on iterators seems magical and mystifying to people. So I thought we could go ahead and demystify that because it's really not that magical. At the end of the day, it's pretty straightforward, but it does make use of Rust type system in a way that is quite powerful, and if you're not familiar with a type system like Rust, a way that might not seem obvious at first, but hopefully today we'll learn that it's actually pretty straightforward. Cool, we had some questions from chat about whether things are muted or not, but it looks like that was just an issue with one person, so hopefully that's not an issue with everybody else. I'm going to switch over real quick to my screen. And the first thing that I wanted to mention is that we have here the Rustaceans station podcast and streaming now Discord channel. For anybody that wants to join that, come on over and join us. I can go ahead now and paste a link to that into chat. So for those in chat who want to join and have a discussion there, we have a chat dedicated to my stream here that you can do, and also a few other streams. And thanks to John who set this all up and is pushing for this. That's really great. And of course, if you're interested in more video content, then there's plenty for you to find in these other streamers' YouTube channels and Twitch streams. Cool. So with that out of the way, today we're going to be talking about iterators. Chat, please let me know if you have any questions at any time. Today's definitely, since we don't have kind of like an overarching goal of code that we're going to be writing, it's really a question forward day, so make sure to ask those questions, because if you have them, then chances are other people have them as well. Cool. So for those unfamiliar, maybe you've only done a little bit of Rust so far, iterators are an important part of Rust. And what iterators is a way to kind of yield values one after another. And so in general, you can think of things like maybe like a collection, like a vector, or an array, or a hash map even, where you have these kind of collection of items and you want to do something to that item one at a time. Iterators are a great way to do that. And iterators are a trait, so we're not talking about a concrete type here, but really a trait where something can implement iterator, and all it has to do is provide a way to yield a new item. The first thing that we should look at when we're talking about iterators here, and let me go ahead and make this a little bit bigger here. The first thing to think about here is the required method next here, and this is really the only required method on Iterator. So when we're creating our own iterator, we're gonna implement next here. What next is basically a way to get the next item in the iterator in the iterator stream. And all it really does is it takes a mutable reference to self, you call it, and then it gives you optionally option self item here. We'll talk about what item is in just a second. So it either gives you an item or it doesn't give you the item. And kind of conventionally, what returning none from this really means is that the iterator is done. There's no more. So you can see here it returns none when the iteration is finished. So basically, when we want to signal there's no more items left, we return none, and otherwise we're returning some. Great. The associated type here, item, is an interesting thing. For those that are coming from languages that don't have generics or don't have kind of really powerful generics, then associated items can be, or associated types can be a little bit confusing. What associated types are kind of in a way a type of generic where there is only one type that is appropriate for a given implementation. And so when you implement iterator on your type's iterator can only yield one type of item. So we can't have an iterator for my type that yields, numbers sometimes, strings sometimes, or something like that. It always has to yield one type of item. Whereas generics are, you kind of like fill in the blank kind of at call time and say, well, in this case, I want it to yield to me, this type, and in this other case, I want it to yield to this type. Iterators don't work that way. They always yield one type of thing. Cool. Great. Any questions from chat or anything like that? Then we can get started. And I think the first thing that we're going to do when we get started is to implement our own iterator trait. So we're going to start from the basics. We're not going to use the standard library iterator. Iterators in Rust are mostly completely just library types. There's not really any special built-in kind of syntax handling for it, with one exception that we'll talk about, or at least I think one exception. But most of what the standard library does with iterators is just kind of plain old Rust that you could implement yourself. And so that's what we're going to do today. Cool. Anything else? Anything from chat or anything like that? We can get started here then. Great. So the first thing that we're going to do here is just create a new project, and I'll just go ahead and say cargo new iterator. And really, it should be a library here probably, but I've gone and created a binary. But I'll show you in a second how we can change that really easily. So I'm just going to open this up in VS Code, and then we probably don't need this anymore. Great. So chat, let me know if that's easy to see or not. Like I said, I accidentally created a binary project here, so something that's meant to be run as a program, but we probably don't want to do that. I do that quite often, where I don't pass the --lib to cargo new. But if you don't know, it's very easy to just change it like that. And then, of course, having this main in here doesn't make any sense, so we can go ahead and delete that. But now we have a library instead, and cargo kind of works with that convention of if it's main.rs, then it's a binary, and if it's lib.rs, then it's a library. Cool. So we want to go ahead and create an iterator. And so the first thing that we're going to want to do is create iterator like this. And then we said that our iterator here, let me go ahead and make this public. Our iterator only has one required method to it. And that required method is next, like this. And we said that it takes a mutable reference itself here. And we'll see why mutable references are a good choice a little bit later on, but kind of the intuition that you should gain from mutable references to self is that we probably we need to have exclusive access to the thing that we're iterating over. And that should make sense. Like as we're iterating over this thing, as we're iterating over it, if we were able to call next from multiple places, we could end up in weird states. So having having the guarantee that next will only be called by one thing one at a time, then we know that that we don't have to worry about certain things like keeping track of if we get next called multiple times, will it mess with some internal state in a weird way. Cool. So, and the next thing here is that it returns an option. So again, if next returns none, that means we're done iterating. If it returns some, then that means that we have more to give then, and we yield the item. And then we have, what are we going to return? So if we were using generics, then we would do something like this, option T or something like that, and we could say that this is T or whatever. But for iterators, we really want to say that there's only one possible type of thing that the implementing type can iterate out from here. And so in order to do that, we use an associated type, just like this. So we say there's some type associated with this trait. We're going to call it item. And of course, if we needed to have some additional guarantees for that associated type, we could put those guarantees here, but we don't need any guarantees here. We just need to know it's some type. We don't know what it is. And what we're returning from next is that item, just like that. So we're good to go here. We should be able to. We should be good to go, and shouldn't need anything else really to get things working here. And just to avoid any weirdness, because we're using the name Iterator here, which there's already an iterator available kind of in scope and stuff like that. I'm just going to call this my iterator, just to avoid any confusion about what iterator we're talking about and stuff like that. Cool. Great. Then the nice thing that we can do now is we can implement this for a given type. And so let's go ahead and say we're going to implement my iterator for vec of t here. And we need to say that we're talking about vecs of some generic type t. We don't know what type t that is. And then we need to go ahead and implement next here. So takes mutable self, and it returns back an option of self item. And we have to say what type of item that is. Now, what type does a vec of t return when it iterates over it? Well, it returns a t, right? So again, this is a little bit interesting, but it should show you that there is only one type of thing that a vec of t can return that happens to be a generic item for that vector. Cool. And let's see what we have going on here. And it's saying that we unimplemented. Cool. So we're done with kind of setting up the boilerplate of the whole thing, and now we just have to go ahead and implement it. But I'm gonna stop right here and wait if there's any questions. Any questions? All right, so there doesn't seem to be any questions from chat right now. So the thing that we should be thinking about right now is, okay, we want to iterate over vectors of t. How do we do that? Well, let's just kind of do some pseudocode real quick and think, okay, we're going to have probably some state of like what current item. And then all we do is just like get that current item, all right? Get the current item and return it back. So this is where we first run into an issue, right? we run into the issue of we need to keep some state here of what the current item is, but where do we keep that state, right? Where do we probably want to keep the like current index that we're iterating off. It will start as index 0, and then we call next, and it will return the item at index 0, and then say, hey, the current item is now going to be index 1. But where do we keep that, right? Where does that actually live? And the answer is it can't live anywhere. We don't own vector, right? We can't add some state. They could have done that in the standard library, where vector kind of kept an item around of how much what current iteration it was on, but that kind of goes against Rust's philosophy of saying, you only pay for what you use. That means every time you have a vector, you are keeping around this state of what item you're iterating on, even if you're not currently iterating. And if we go back to the standard library here, and we look at vec real quick, and we can scroll down here, scroll over here, and we can see here this trait implementation. So these are the trait implementations for vector in the standard library. And if we try and look for iterator here, we're not going to find it. Now we see this IntoIterator thing that we're going to get to in a little bit, but we don't see an iterator right here. And that's because vectors are not iterators. You cannot directly iterate over a vector at all. And you might be wondering something like, okay, Ryan, but I'm writing some Rust code here. I got my main function. I've got some vec called myvec. Let's go ahead and create that real quick. 1, 2, 3. And then I can iterate over that vector. That's really easy. I just say, for item in myvec, just like this. And I can go ahead and print out the item here. And this works. This is the one piece of kind of built-in like language support that our iterator-related types that we're going to be talking about today does kind of on its own. But just before we get there, the first thing to realize is that when we do this for item in myvec right here, we're not actually iterating over the vector itself. Or let me rephrase that, because we are iterating over the vector itself, but we're not, the vector itself is not the iterator that we're using to call next on. So we're not calling next on vector. Vector doesn't have this next method on it. It does not implement iterator. But rather there's some kind of extra little tiny bit of magic going on that we're going to talk about in a little bit that allows us to do this. But we've just discovered why vector does not implement iterator, because there's no place to keep track of the state that we need to when we're iterating. And this is important to know because there's oftentimes where you want to implement iterator for your own types, and you're going to have to think, is my type actually the thing that I want to like implement iterator on, or is there some other type that I want to implement iterator on that keeps track of that extra state that I need to? And the answer is not always, but quite often, that you want to create another type that is the actual iterator type that implements iterator. And we'll do that in just a second. Chat mentioned something that's true. We could have, instead of unimplemented here, which unimplemented, by the way, is a great thing. It's equivalent to to-do. To-do is just shorter, and it's newer. And I'm still in the habit of writing unimplemented because to-do didn't exist back in the day. Both of them basically kind of tell the type checker, like, all this stuff, like, just trust that it type checks, don't worry about it. But if you were to, and compiling the code works fine, but if you were to run it and it reaches to do, it panics. And so this is a great way of saying, like, I just want the thing to compile, and if I run it, it's fine to panic and crash or whatever, but I want it to compile. And this is really great for kind of intermediate steps inside of your code. and chat was saying it's easier to write, which it certainly is. So unimplemented is probably, not really useful anymore. But I'm in a bad habit of using it. Cool. So we've just discovered that creating my iterator for our vec type here is not actually going to work because we don't have any place to keep our extra state here. And so what we're going to have to do is a common pattern here. We're going to have to create a new type, and we'll say something like struct my vec iterator. It's going to have some stuff in it. We don't know what yet. And this myVec iterator thing is going to iterate, is going to be the iterator that actually we implement my iterator for. And it will have, it will be able to keep the current state. So we can do that real quick, where we can say myVec iterator instead of iterator. And it's probably going to be generic. That's a good point, because we want it to hold on to generic vectors, right? So it's going to have some type T. And then for now, we'll say, okay, like it's going to iterate over a vector. So like, why not we just keep a vector in here, right? Like, that's cool. We got a vector in there. That's great. And the item that we want to iterate from our vec iterator is going to be the T that our vector is holding onto. And we can say now, like, okay, like what's the current item? So like let current equals, and this is some state that we're going to have to keep here. So like current or like current index maybe is a better name. So we want to keep like the current index that we're iterating over here. So we get the current index, and then we want to like what's the current item index. Then we get the current item. Let's do this under here. So current item is self.vec current. This, and then that should work, right? So this doesn't work for several reasons. The first one that we get here is that we're saying, hey, I expected an option here, and you're giving me back a T. And that's true, right? We are, when you call self.vec with the brackets here, it returns back an item. It returns back the type T inside of there. What happens if there is no item at the index that we pass in? It panics, and so that usually works great. And we can do something like this. We can just wrap it in a sum here, and that will, it doesn't work but for other reasons, but this kind of satisfies the type checker in this instance. That we're returning back an option here. So that's good. Or what we can do instead is say self.vec get instead. And get is just like the square brackets there, except that if there is no item at that index, it returns back an option. And so we can say current item. Oops. Cool. All right, so here's where we're going to run into an issue here. When we return back, when we call get on our vector here, it is returning back a reference into our vector. And the reason for this is I like to picture it in my head is, when we call get on the thing, we don't actually want to like pull the item from the vector's memory and hand it to the user and say like, here's the item, I ripped it out of the vector and I'm giving it to you. Instead, what we want to do is say, there's a vector, some memory with some items in it, and I'm going to give you a pointer, a reference to that item, and say, hey, it's over here, it lives over here, here is the reference, here is a pointer to that thing. So I'm not going to give you the thing, but rather just tell you where in memory it is. And the reason for this is because we're simply borrowing the vector right now. And what we want to do is is not kind of mess with the vector itself. We simply want to iterate over it by giving kind of views into it. And so we don't want to rip the item out of the vector, but instead we want to just tell the user of this API, the item is over here. It's over in this direction. This is where you can find it. And that's exactly what Git does here. It returns to us and because it's not compiling, I'm not getting the pop-up anymore, but it returns to us a reference to the item inside of there. So it doesn't rip it out of the vector, it just simply says this is where it is. And this is pointing to kind of a fundamental flaw with what we've said so far. What we've said so far is that our iterator is going to return back T's. It's going to return back owned copies of the items inside of the vector. Is that what we want? That is certainly a possibility, and in fact there are APIs for doing that, where we iterate over a vector and kind of consume it as we go. But the kind of standard iterator on vector, the thing that we're emulating right now, is usually returns back references. So it doesn't consume the collection it's iterating over, but rather just says, okay, here's a pointer or reference to the first item, here's a reference to the second item, here's a reference to the third item, and just simply returns back references to you. And so what we've said here in this item equals T is, in that case, is a lie. What we really want to say is we're returning back references to a T here. Cool. Great, I'm going to stop right here where the code still is not compiling, just in case you can't see. There's a little squiggly line right here about lifetimes. So we're going to get into lifetimes now. But I want to stop and check on chat real quick. Cool. Chat said the macro source code for to do and for unimplemented are the same. And I'm pretty sure they're exactly the same. Then there was another question about does this right here with Git do bounds checking on every iteration? It does. Now it might be possible for the compiler to elide those bound checks. It might be able to tell that it doesn't have to do bound checking here. My intuition is that it wouldn't be able to tell. So yes, it would be doing bounds checking here. There are ways to get around that, including unsafe code that we could write. We'll see if we get there. We might not today. And then chat was saying Git will return none if out of bounds. That's true, but it has to first check, is it out of bounds? And that's how it knows to return none, is it first checks the bounds of the vector and sees if the index that we're passing in is actually correct. Cool. Okay, so our code is failing to compile here, again about needing a lifetime specifier. You may not understand why this code needs a lifetime specifier right now, but in those cases, just listening to the Rust compiler and saying, hey, I need you to introduce a lifetime specifier here, we can just go ahead and do that and see what happens. So using tick A as the kind of normal generic lifetime that we're specifying here. And of course now it says, I don't know what tick A is. You're introducing this lifetime parameter, but I don't know what it is. And this might be kind of leading us down a path that we weren't sure we were on before. So we have, tick A here. And then we have tick A here, but what we're getting another error that's saying, hey, you've specified a lifetime parameter, tick A here, but it's not constrained by anything. And this is an important point that you'll run into sometimes when dealing with generic code here. The generics here have to be used somewhere in here. If they're not, like we're using tick A down here, but that doesn't matter to the thing. The generics have to be used by either our type here, or the trait that we're implementing it for. And so the question is, okay, we have a lifetime of the type that we're iterating over it, but what relation does this item that we're iterating over it have to the item to our struct here, myVec_Iterator? And there's various ways that we could go about solving this, but let's take a look at myVec_Iterator here real quick and think about this. We want to be able to iterate over our vector and yield references to the items in that vector for a certain amount of time, for a certain lifetime, and that lifetime is tied to however long that our vector lives for. And in fact, like, one thing that we could do here is say here we have myVec_Iterator is constrained on some lifetime tick a here, just like this. But then we get the same problem up here, like, hey, you're using tick a here, but you're not actually, you're declaring it up here, but you're not actually using it anywhere in here. Now this is really where we can make a decision about how we want to do this. But let's think about myVec_Iterator here. We have ownership over the vector. That means when we get an iterator, a myVec_Iterator, it means it owns the vector. So when we're done with myVec_Iterator, we're going to drop the vector. We don't need the vector anymore. Is that typically how we use vectors in Rust? No. Typically what we do is we say we have a collection, we call iterator on it, we can iterate over it, but then we could still use the vector afterwards, right? We were just taking a peek inside of the thing, but we don't want to get an iterator over it, get some references inside of it, and then once we're done with it, kind of just drop the thing. So really, we don't need ownership over the vector here. We simply need a reference to it, to the vector itself. And so we can do this here. And this is, and you'll see the code compiles now. This is important. What we've basically said here is that there's some lifetime that we need a reference to t to be viable for. It's generic here, but that is the same lifetime when we kind of fill in all the blanks here as to how long we're borrowing the vector for. So what we're saying is we will not have references to t's for longer than however long that we have a reference to the collection as a whole. And that makes sense, right? If we were able to have references to t's for longer than we had a reference to the vector itself, that means somebody else could drop the vector while we still have references to it. That would be a use after free bug, right? But what we're saying here is our iterator is getting items, is yielding references to our t's for some lifetime, and that lifetime is the same lifetime as however long we are holding on to a reference to the collection as a whole. Going to take a second here. Lifetimes are usually the most confusing thing to people, but just think about how, we need a reference to type T. Wouldn't it be a terrible thing if we had a reference to a type T inside of that vector when the vector was dropped and the memory was reclaimed? That would be, that's use after free. And so we're tying the references that we have to the items inside of the vector to the lifetime of however long our reference to our vector lives. I'm going to stop for questions real quick to see if there's any from chat. Doesn't look like there is. Hopefully this makes sense to everybody. Cool. Great. Okay. So so this doesn't work, right? But if you look at the implementation of Next, probably you can see why it doesn't work. But let's go ahead and write a test for it anyway. So down here, I'm just gonna say that mod tests use super, and then we're gonna create a test here, and we're gonna say it works. So it's usually a good one. Let me scroll down for everybody. So now we are going to say that we have a vector. And we want to iterate over that vector. How do we do that? By getting an iterator. So my vec iterator, I think is what we called it, right? My vec iterator. And it has a reference to the vec here. And it has the current item. And the current item starts off at 0. Did we call it current index is what we called it. And if we want to iterate over it, we just have to constantly call next on it, right? So we can say, while let sum here is equal to iter.next. So we're going to call next in a loop basically, and as long as it returns back the pattern sum, we can get reference to the item. And here we can say print line item. Oops. Cool. And we have one issue here where we cannot borrow iter as mutable because we haven't declared it as mutable. So we're calling next with an ampersand mute here. So we're mutating our vec iterator here, and so we have to declare that we're mutating it here, just so everybody's aware that we're going to be mutating it. And we should be able to now do cargo test, and it's looping forever and ever and ever and ever, right? And maybe you can't hear my computer, but the fan just started to go up. And if we look back at our code here, it should be pretty obvious what's going on. We're getting the current index, we're getting the item from the vector, right? And then we're never incrementing the current index. So that's probably not very good. So we want to go ahead and do that. And we'll increment it by 1. And we can run it again. And it passes, but we're not actually testing anything, so we can go ahead and do no capture. And no capture on test simply by default the test runner and Rust kind of slurps up standard out, and so if you're printing something in your test, you won't see it unless the test fails. But if you want to see it when it passes, then you can pass this no capture item, and we can see here we get 1, 2, and 3, and then we end. So it looks like we're passing. Great. So looks like we have things working here. This isn't the best API ever, right? Where we have to kind of create an iterator that has a vector, but this is basically how it works in the standard library. We can, we don't own vector here, so we can't really directly add a method to vector because vector is part of the standard library. But there is a way to kind of add things to types that you don't own after the fact. There's a pattern that we can use in order to do that called extension traits, where we can say that we have a trait, and let's call it like my iterator extent, just like this. And it's going to have one item on it called like my iter, and it returns back a for now, we'll just hard code it to be my vec iterator, just like that. And we have to add the generic types here. And so we can say that our trait is generic over type T, and it's tied to the lifetime A here. Okay, so we've created this trait, and we're going to implement this extension trait on vectors of T, vectors of any type T. And what we're effectively doing here is adding this myIter item to any vector out there, which is really great. So we've effectively extended a type that we don't own, not by inheriting from it or something like that you would do in classic, object-oriented programming, but by implementing a trait on this type. Great. So then we can say myIter, and that takes self here, a reference to self, and returns back a myVec iterator. Of course, say this here. And then effectively, all we have to do is just kind of take this right here and move it on up here and change our vec to self. And then, now we've implemented this myIter, and we don't have to do any of this jazz here, where we can just say vec dot myIter. And hopefully this works. Oh, and it doesn't. And the reason for that, of course, is that we are calling this while loop over and over again, and we're calling vec myIter. So we're getting a new iterator on each loop, which is obviously not what we want. So what we need to do is still have this iter here, so that we just get one iterator and not one on each loop. And this will work. Cool, and it does. So again, this is a common pattern that you have in Rust. If you want to extend a type that you don't own, which we don't own the vec type, with your functionality, you can come up with an extension trait and add methods to your type after the fact. And any user that wants those methods, all they have to do is have this trait in scope, which we do. We have this trait in scope down here. And when we have the trait in scope, then we're able to use the methods that we define on that trait. Cool. So that's good. We have re-implemented Iterator here. We've re-implemented the iterator trait, called it myIterator. We have discovered that we don't actually iterate usually over the collections directly, but rather create new types that can keep track of the state needed for iteration. For instance, in the case of vec, what the current index that we're on is, because we don't want to have that current index sitting on our vector at all times. If we don't iterate on the vector, we don't want to pay the price of having that extra number attached to the vector. And so what we do is we create a new type called myVec iterator in this case, and we implement iterator for that new type. And all that iterator is this next method where we call it and we return back the item. We return back some of the item when we have it, and when we're done iterating, we return back none. And we implemented this iterator trait, which allows us to kind of wrap this all up. And in fact, in case you're not aware, in vec, if we go here, you can see where is that defined? Here it is. So on the standard library vec, we have iter here, and that returns back this iter struct, which you can see here. This is standard slice iter. And it is this iter struct that implements iterator over slices. And because vectors can be turned into slices, we use the same thing for vectors and for slices here. So it's a little bit more flexible in the case of the standard library, but ultimately the same exact thing. And we can see down here in, where is it? Here. Here we can see that Iterator is implemented for iter. And honestly, for me, the toughest part about keeping all this straight in my head is that the naming for this, because it's not normally, you don't normally read these names, the naming is not that great. And so you have implement iterator for iter, and it's like iter of what? Iter of type T? No, it's actually iter for slices and stuff like that. So it can be kind of confusing, but this is effectively what we've done today. Cool. Awesome. And yeah, chat was saying that iter is a method on slice, which is exactly true. Great. Any more questions from chat or anything like that? No. All right. Then the next thing that we will do is the unfortunate part is that we will not be able to do something like for item in vec like this. We will not be able to do that in a way that works with our iterator type. But we should be able, cool. I believe what we will be able to do is take advantage of the kind of built-in magic of for loops in Rust that allow us to write this code and have it work. And so we said before that this code right here works even though we've already seen that vec is not an iterator, which is kind of strange, right? Like we're iterating over vec. Like we haven't called anything here. We've not called any .iter or anything like that here on our vector, but yet we're still iterating here. This works totally fine. And that's because what for item in vec does here is really it kind of desugars into this. Just like that. Or in fact, it might be IntoIterator, I think. Yeah, there it is. And so this and this here are equivalent to each other. One is sugar for the other. So every time you're using a for loop, basically what is happening on the thing on the right side is it calls .IntoIterator on it and gets an iterator for that item. And so for vector, we're calling IntoIterator here. And in fact, since we know that that's the desugaring, we could do something like this and get this to work. Not mitter, but my iter. So as long as we get this to work, then we'll be able to get the regular for loops working as well. And it's saying, here it's kind of hard to read in this output, but it's saying like there's no method IntoIterator on this myvec iterator thing, but it does exist. IntoIterator does exist. The compiler is smart enough to say, hey, there's something out there that where IntoIterator exists on, and you could implement that trait on your myvec iterator. Let's see if we do this here, maybe it's a bit clearer. Yeah, you can see here saying there's no method IntoIterator. It does exist, but the following trait bounds were not satisfied. So it's saying that, you know, myvec iterator is not an iterator, and ampersand myvec iterator is not an iterator, and ampersand mut myvec iterator is not an iterator, which is required by, all these are required by this IntoIterator thing that we have here. So really what we have to do is go over here and IntoIterator and take a look at this. So IntoIterator is another trait, which if you implement it for items, it's specifically for turning that item into an iterator, hence the name IntoIterator, right? And you can see here that it even mentions the point that we mentioned before, where this is what allows your type to work with the for loop syntax in Rust. And if we come down here and take a look, there's two associated items that we have here and one required method. So we can work through this and actually implement IntoIterator for our type here. And we'll talk about what the various items are then. So again, we want to implement IntoIterator for our myvec iterator type here. And so we can say impl IntoIterator, and I believe that should work. And it's going to be for some lifetime A and some type T here. And let's see what it's complaining about. Oh, it's complaining here that we need to say, hey, what are you talking about, tick A? I don't know what that is. Well, it's some generic tick A, and it's some generic T here. And then it's going to complain and say, hey, you're missing a whole bunch of things here. You got to let me know the item that you're iterating over. You have to let me know the type that you're turning your iterator into, and you have to implement this IntoIterator thing for it. And so we can just kind of copy this here. And say, we can use our old friend to do here just to get that to work. So we have the function, and look, it takes a self, which that is interesting, and we'll talk about that in just a second. It takes a self and returns back this IntoIterator associated type. So what is the IntoIterator here? Well, this doesn't quite work, right? We are saying that we want to take the self and return back an iterator. What is the iterator that is associated with the myvec iterator? Well, turns out it's self, right? So type IntoIterator. How do we turn the myvec iterator into an iterator? Well, we turn into it by returning self as the iterator here. Or we could say myvec iterator, just like that. We'll get to this in just a second. And what is the item that we're iterating over? The item that we're iterating over is the type T. Now we have one problem here. It's saying, hey, myvec iterator is not an iterator. And that's true, right? Myvec iterator is a myiterator. The whole thing that we're kind of, we are pretending to be an iterator through using myiterator, but in the standard library, IntoIterator here assumes, or demands rather, that the type that we're turning into an iterator is itself an iterator. It has to be, right? That's kind of the whole point. We want to take the type and turn it into an iterator. Well, that iterator better well implement iterator. That makes sense. If this wasn't here, then we could return any type, whether it actually yielded an iterator or not. We wouldn't know. But this enforces and says the thing you're returning back from IntoIterator is actually an iterator. But of course, my back iterator here is not an iterator, it's a my iterator. We should be able to fix that rather easily using another old trick that is quite common, where we say, I'm going to implement iterator for any type t where the type t is my iterator. Oops. And that requires next. Which returns back a option of self item. So we're sort of we're implementing iterator for my iterator here. Self item, right? This is just the standard definition of an iterator, and of course we need the associated type item. So what is the item that we're iterating for any type t that implements my iterator? Well, it's my iterator item, right? Just like that. This won't work though, because it's like, I don't know what you're talking about. Which my iterator? It's a trait. So we have to use this weird syntax here, which says the type t as a my iterator get its item. Oh, and this, unfortunately, I think ends up screwing with already. Let's see if we can get a better look at the error message. We might be at the end of the road here. Sorry. Cargo check. So now we're running into some conflicting things. There's a conflicting implementation saying that conflicting implementation in core where IntoIterator is already implemented for iterate. Oh, this is actually fine. So we're getting a thing which is saying in the standard library, or in the core library actually, there's an implementation for IntoIterator for any type I where I implements iterator already. So what this is saying is IntoIterator already knows how to turn iterators into iterators. It knows that relationship. And that makes sense that they have that, right? Anything that's already an iterator should be able to be turned into an iterator itself, right? And so all we have to do now that we have an iterator implementation for any type t that implements my iterator, we can get rid of this. And let's see what it's saying now. So and this is an issue now that we're running into, where we are running into the orphan rule, where we're saying that we need to implement. We're trying to implement iterator for any type t. We don't know what that type is. We don't own that type necessarily. That's any type in the world as long as it implements my iterator. And it's running into an implementation where that already exists in the core library. There are ways around this that we're already getting kind of into the weeds here of that is not really iterator related and stuff like that. But in general, what you should be able to see here is that if we can implement IntoIterator on our type, then we will be able to use it in the for syntax. So we'll stop that for now. Cool. And of course, this no longer works. Great. So I'm going to stop real quick. That was a lot right there. Just to reiterate real quickly what we talked about. We came up with our own iterator trait. We called it myIterator. It's exactly the same as Iterator, except it kind of lacks a lot of functionality. And then we implemented a myVecIterator for vector that implements this myIterator trait. So we're sort of doing the same thing that vector already has with the standard slice iter type, which is the iterator for slices that's already built in, that implements the iterator trait. And we learned about how to use extension traits here in order to extend types that we don't own. We wanted to create a function on vector, or a method on vector. We don't own vector because it comes from the standard library, but that's no problem. We can create an extension trait that simply adds the myIterator, or the myIter method to vectors for us. And as long as users have myIterator extension in scope, then they will have access to this myIter method as well, which is really great. Cool. Any more questions here? Awesome. I think the next thing that we will do is implement map on our myIterator that we have here, and see what that functionality looks like. If we go here and look for map, we should, where is it here? So map is kind of a built-in iterator method. And so on traits, right, you can have required methods where you require that people implementing that trait implement this method. And then you can have kind of default methods, which are, if you don't override them, they kind of come for free with the trait. And map is one of them. What map does, if you've not used it before, is pretty simple. You have an iterator here. You have a collection 1, 2, 3. You get its iterator by calling .iter on the slice, and then you call map, and it simply does the thing in the closure to each item in the collection. And so 2 times 1 is 2, 2 times 2 is 4, 2 times 6 is 2 times 3, sorry, is 6, and then we're done. We get none here. And so we should be able to implement this ourselves. It has a funky signature, but the signature is actually pretty straightforward when we go through it. Cool. Let's do that real quick. So we're going to implement map, and if we look here, what map does is it takes self here, and it takes a function of type f. We'll talk it there. And it's important to note that it takes self here, right? Because when we're mapping over an item, we no longer we don't want to have the iterator that we had before. We want to have a new iterator that is the result of mapping our function over each item in the thing. So we no longer will have the previous iterator, we've consumed it, and now we have a new iterator, and that iterator is going to be some type, and we'll call it myMap to follow the convention that we had before. And just like in the standard library, myMap is going to take self here, and it's going to take the function that we've passed to it. And presumably we will implement iterator on myMap. So we're still able to iterate. And now we have to say what is this f type here? Like we've not specified what that is. Well, f type is just some generic type f. We don't know what it is, except that we know that f implements this closure type here. So f is a closure which takes the item here, and returns back some type B, just like that. So the function takes the item that the iterator is yielding, and it returns back some other type, some type B. And again, we know nothing about type B. It can be literally anything. And we use our old friend to do here. All right. So we have a couple of issues here. One is that the size of values of type self cannot be known in a compilation. So this has to do with the fact that traits can be implemented on traits, or implemented on things where we don't know the size of it at compile time. But in order to move an item, we have to know its size because it's not behind a pointer. And so we don't know what we've basically said here by default, but when traits, we don't know the item that implements this trait, what size it has, how much memory it takes up, basically. But in order for us to move self, we have to know concretely what size it actually is. And so for now, what we can do is do this, where we say that whatever implements my iterator has to be sized. This is not the best way to do it, but this is just a simple way to do it. Where whatever implements iterator, it cannot be an unsized type. It cannot be a type that we don't know the size of it at compile time. And most items in Rust are sized. So vectors, we know exactly how big a vector is at compile time. It's 3 words big. We know exactly how big an array is. We know exactly how big a string is. We know exactly how big on and on and on. But there are certain items that we do not know the size of, and we can't use my iterator for those types. And now the last thing that we have to do is create this my map thing. It doesn't know what my map is because there is no my map. We have to create it. And my map is going to take two types here. We'll say one type I and one type F. And we're going to say that it takes that the type I, we're going to call it Iterator, and type F is going to be some funk. And we got to save the file, of course. Cool. Cool. We've said my iterator is public, but we're leaking a private type here because my map is not public, so we got to make that public. That's all that was saying. So hopefully this is a quite complicated method signature here, but hopefully it makes sense. We're taking self by ownership. Why are we doing that? Because we don't want to continue iterating on our previous iterator. We want to turn it into a new type of iterator, namely my map. We want to turn it into an iterator that maps over things, that calls a function on each item and gets a new type of item out of it. So that's why we take self here. We had to change our trait to only work with sized items because we're moving self here, and you can only move items that you know the size of. F here is some function type where we say that F is a closure. It's a mutable closure, meaning it can possibly mutate state inside of it. It takes one argument, whatever self item is, and it returns back some type B. We don't know what it is, but it returns it back. Cool. And then this should be relatively easy to do. We just got to say, my map, and iterator here is self, and func here is f. And there we go. So this is done. We should probably write a test real quick where we say let iter is equal to vec myIter. So we're getting that our myIterator type, my vec iterator type that we've gotten before. You can see here. Doesn't show us obviously. But we want to be able to do something like this, where we say dot map, and we'll take the exact item that we got from the docs, where we multiply it by 2, just like this. And we can now say here, we should, and if we go ahead and print this out, line, like this, of course we gotta declare this to be mutable since we're gonna mutate it. We should hopefully see, what is it complaining about here? Ah, of course. It doesn't work. It's not compiling. Why? Because there is no type next on our mymap thing here, right? It doesn't have a method called next. And the compiler is trying to be helpful here and saying, hey, I've got some traits that I know about that have a next method on it. Maybe you should implement one of these traits for your type so that you can call a next method. And we've got things like standard iterator. That's probably a good one to do. We've got this, pattern searcher thing. We don't need to worry about that. And myIterator also. So our custom type here, it's aware of that. And that's what we're actually going to do here, is implement myIterator for my map. And we know exactly, we need my map of I and of F. So we need some type, we need to know what the item is right here, and then we need to implement the next method again. Cool. So what is it complaining about? Well, first thing right here, for I, it's like, I don't know what that is. What is I? Please tell me. And so we can just say, hey, it's some generic parameter. We don't know what it is. And then it's saying, hey, like, what is type F here? I don't know what that is either. And we can say, hey, okay, it's also some generic parameter. Please shut up. So now we've shut it up. But we're getting a thing here. It's like, hey, you got to provide a type here. What is the type that item is? We got to say things like this, where we want to say something like item, right? I is an iterator, right? We want its item, right? Well, guess what it's saying? It's like, I don't know what item is on I. Why? Because it doesn't know what I is. I is any type out in the entire universe. It could be any type. It could be a U32. Does U32 have an item associated with it? No, it doesn't, right? Only types that are iterators have that. So what we can do is say I is actually, I is a myIterator. And then it knows, oh, I is a myIterator. Well, then I will take the item that its implementation for myIterator provides, and that makes sense. So what is item here? It's whatever item is for the myIterator implementation for type I. We're all good there. Cool. Okay, so how do we do this? Well, when we call next, what we want to do is call next on our iterator, right? So iterator dot next, right? And this compiles, like, because basically what we've now defined the semantics of my map is a wrapper around our iterator. It does nothing differently, but that's not what we want, right? What we want is to call this function that we have with the item. So we need to get the item back. And we have this nice question mark operator here in Rust, which can say, hey, the type that you're returning back from next is an option. If it's none, return that back from the function, and otherwise put that item inside of here. And so it effectively unwraps our option that we got from next. If it's none, returns from the function, and otherwise, if it's sum, it unwraps the item inside of the sum and puts it inside of our variable item. Cool. It's complaining because we haven't finished our implementation here, but I bet you if we were to use our old friend to do here, it would. Cool. So it's just complaining, hey, it didn't finish the implementation here. So now we have the item here, and we want to call the function with that item. So we can say self-func here and pass in the item. And then, we get back to the item, but we need to return back an option of that item, an option of it. And so what we should do instead is we need to rewrap it in sum here, like this. Cool. So it's not working. And hopefully that it should be fairly obvious what is not working. It's the same exact problem we had before up here, where we're saying call our func here, but there's no method name func. It's like, what is func? I don't know what func is. Like func, I don't have a method name func, and we're like, no, we mean this thing. But really, it's like, okay, well, maybe we need to come in here and do a little bit of syntax change or whatever, and really get the thing called func and then call it. And it's like, I expected a function, but I found f. Because all we've said is that we have some type f. And again, f could be any type in the world. It could be I don't know, it could be U32, it could be a vector, it could be a string, and obviously you cannot use call syntax on a string or a vector or U32. So we need to constrain f and say, no, f, by the way, is some type. We don't know what it is, but we do know that it implements this closure trait. So we can say here that f is an fn mut, and it takes a I item here, whatever the item is on I, and it returns some type b here. And now we don't know what b is, so we have to say, okay, it's b here. And this works almost. It almost works, right? We've got it. So we have some type b that our function f returns. We don't know what it is, but we've screwed up a little bit here, because what we've said is that the item that our mymap iterator returns is whatever type that I item returns. And this would work if we were to say something like this. This works fine, of course. Now it's like, what is b? What is going on? Oh, because of this. We had a semicolon, a rogue semicolon. So this works. This works totally fine, because what we're saying is that the function that we call for every item that we get takes in whatever type the kind of iterator, the associated iterator that we has, and it returns back the same type. And this should work fine down here. Why is it? I'm not exactly sure why it's not, test, sorry. Of course, yes. So this is actually the issue in general that we're running into, and we're already running into with this example, because we're returning back references instead of own things. But let's make it a bit clearer what's happening here. X here is let's give it concrete type. We should specify that these things are, let's say they're U sizes. All these are U sizes. So X here is going to be a reference to a U size. Because when we're iterating, again, we're not returning back own values, we're returning back references. We're returning back pointers into the original vector, saying, hey, it's over there, right? But what we've said here, so again, the associated item of our iterator is a reference to a U size. But what are we returning from here? We're returning back a U size. We're multiplying our number times 2 and returning back a U size. But we've said that whatever we return from map has to be the same exact type that we passed into it. So whatever type this is has to be the type that we return back from here. But we're not doing that. We're returning back a U size, not a reference to a U size. And this is quite clear when we do something like, I don't know, let's do X to string. This is also not right, and probably a little bit more clear to see, because we're taking in an ampersand U size here, but we're returning back a string. But up here, we've said that the type that where is it again? Sorry, here. The type that we take into the closure is the same exact type that we will return from the closure. But we don't want to do that. We want to be a little bit nicer than that. We want to say that, I believe I can do this here at the end, the closure can return whatever type it wants to. It's going to return any type B. But then now what we have to say is that our item here is actually B. And this works now. And look, it's all compiling. So it doesn't matter what we return now from our closure. Whatever, the thing that my map iterator will iterate is whatever type we return from the closure. Whew, this is a lot. But this is kind of deep guts of iterators here. If you understand this, you can probably implement iterator for any type that you want to. I'm going to take a break for a second and look at chat and see if there's any questions that we have. So we have somebody who's saying that the syntax of type item ampersand tick AT is way over my head. I will stick with C#. I'm not going to say that you shouldn't stick with C#. That's totally fine. I would encourage you, and I hope that you will stick through it. There's a reason that the syntax is complicated, because what we're expressing here you cannot express in C#. C# does not have these concepts. So of course it doesn't have the same syntax. C# is easier in that way, which is a good thing. And I'm not disparaging C#. C# is great. Like C#'s awesome. The reason that this syntax exists in Rust is because we have to be able to express concepts that we do not need to express in C#, because C# has a garbage collector. And so the reason for this is because we need to be able to say that the reference that we're taking to our type T right here is tied to the however long our vector lives up here. And in C# you don't have to care about that, because the garbage collector will ensure that that's the case. Rust, you pay this extra cognitive load here, which absolutely it is an extra cognitive load for the fact that you don't have to run a garbage collector. And Rust will ensure that you will never make the mistake that you can make in C, for instance, where you might use this reference after your vector has been freed, which is the cause of a lot of bugs, including some very malicious ones. So I hope that's fine. If your choice then is to continue with C#, that's awesome. Like, that's not a bad a bad choice to make. But I don't want to discourage those who are interested in learning Rust away from the language just because of the syntax. It is a little bit gnarly at first, but it's there for a reason, and hopefully, the more that you use it, the clearer it becomes why that syntax has to exist. Cool. And then yeah, so Chad is also saying it's kind of fun, sad that the basic stuff we're playing around with runs into loads of rough edges and odd syntaxes that we don't have to otherwise deal with. I don't know if this is necessarily basic stuff. Implementing your own iterator is definitely an intermediate concept. Like if you're just starting out with Rust and wanting to write like a basic app or something like that, you can get away with not having to write your own iterators from scratch, and especially having to write your own, iterator, clone here that we've done here with my iterator. That obviously you would never have to do because iterator already exists. This is not exactly basics. I would not classify it as that. This is something that you will only run into when you start getting into intermediate, or even in some cases, some of this is slightly advanced. Great. Any other questions about what we've done so far? There's another question about what are the real benefits of not using a GC in Rust. So that's a very big question. If you are in a field where garbage collectors are acceptable, then so you're writing, a GUI app, let's say, like a basic app, or a web server or something, a web service, I should say. Garbage collectors are totally fine and totally great. Like there's nothing wrong with garbage collectors by any stretch of the imagination. There are some use cases out there where a garbage collector is either completely not viable or, depending on the load that you're dealing with, not acceptable. So let's take games, high performance games, for instance. In high performance games, you need to be exactly sure when everything will run, and if you have a random pause due to a garbage collector, you will probably run into to a lot of issues. Now, that being said, plenty of people write games in C# and it works fine. So it's not every single game, but your kind of blockbuster games need that performance to kind of push the envelope, and that's why you tend to see them written in C++, for instance, because they can't afford the price of a garbage collector that you would find in a language like C#. If you're writing an operating system, same thing. I work at Microsoft, and we don't tend to write low-level operating system components in C#, not because we don't love C#, but because for some of those components, having a garbage collector would impose too much of an overhead for us to be willing to pay that price. And so for that, we use C++, and nowadays are starting to also use Rust as well. I think the answer is if you're working in an area where you can't imagine why you wouldn't use a garbage collector, then you're right. You probably can use a garbage collector, and I would only encourage you to learn Rust because it's a fun language. I enjoy writing it. I know a lot of other people do, and it allows it teaches you a little bit more about things that you wouldn't have to think about in C#. So you're probably going to end up learning it. But will you need it for your day and day job? If probably not, and that's fine. Hopefully that's a good enough answer. And if the answer of it's just fun to learn a language sometimes is not good enough, then I don't know what to say. It's good enough for me. So cool. We have about 25 minutes left of what I wanted to do, and so I really wanted to get to our last point, and that's to talk about collect. Collect is kind of I think the method on iterators that people most talk about as being kind of somewhat confusing. Not because it's not because its usage is overly confusing, but because they are not sure how it works. It seems somewhat magical. If you've not used collect before, basically what it allows you to do is take an iterator and turn it into some sort of collection, usually. So here we are iterating over a slice here, or an array, multiplying it by 2 using our old friend map, and then we call collect on it, and what do we end up with? We end up with a vector of I32s here. If we didn't call collect here, we would just end up with that kind of map struct. We would still have an iterator. And by the way, this is super important. I can't believe I didn't mention it before. Iterators are lazy. They do not do anything until you actively iterate over them. And how do you actively iterate over them? By using a for loop, by calling collect. Something has to actively call next on it. If you don't call next on the thing, then it will never get run. And so without this line, our iterator will never run. Nothing will happen. We need to call collect on it to actually run the iterator and collect it into this vector. And yes, Chad is mentioning turbofish. We will get to turbofish in a little bit. It's I usually vehemently disagree with people who think that Rust syntax is ugly, because I don't think it is at all. The turbofish is weird, though. That is one point where I will definitely say its syntax is a bit strange. Cool. So we're going to implement collect using kind of our own types. We're going to re-implement the idea of collect. And so collect is just like map. Collect is a method on iterator that you get for free if you implement iterator. And so up here we can implement collect. Fn collect. And what does collect do? It takes self, just like map, for the same exact reasons. We want to stop using the iterator before and create a new type of iteration or new thing. And it returns some type that they call B here. And the important part, and the whole reason that collect works, is this part right here. This where clause here. So collect doesn't just return any old B, it doesn't return some random B that, can be anything. It returns B where B implements this from iterator trait. So from iterator, and from iterator is generic, and from iterator takes whatever the item of self is. So we'll look into this in just a second. Cool. And from iterator is not available by default. You have to, I think it's in standard iter. That's why I was complaining there. Oops. Cool. And of course, while we're talking about it, we can use our old friend to do here. So this is great. We've got our signature here. We will now be able to turn our iterator into any type B. Doesn't matter what it is, as long as it implements from iterator. Let's take a look at from iterator real quick. So as the docs say, this is converting from an iterator. So this is sort of the dual of IntoIterator. We had IntoIterator before, which took some type and turned it into an iterator. And now we have an iterator and we want to turn it into a type. So it's the kind of the opposite. And it has just one required method on it, from iter, right here. And it creates a value from an iterator. So you can see here, we have vec from iter, and then it takes an iterator and creates a vec from that. And so this should be fairly straightforward to implement. What we can do is say, How do we do this? So the challenge here is that we're using this from iterator type, which obviously works very naturally with the built-in iterator thing, which is really great. We are dealing with our my iterator thing, so there's several ways that we could go about this. We could add functionality that turns our my iterator into an iterator, which we tried before, without too much success. I think what a more instructive thing would be is to go the route that we did before, where we're going to implement the from iterator concept exactly, from scratch, where we're going to have our own from iterator trait, which we're going to call my iterator from iterator, sorry, and it's going to work exactly the same way as before. So this will help us understand what's going on. Cool. Okay, and you can see up here from iterator, if we look at the source here, from iterator takes some type A. And it's sized, of course. Well, we'll talk about that in just a second. So cool. What is it complaining about up here? We're leaking a private type because we didn't make this public. Okay, so let's go over this real quick. My from iterator takes a generic type A, and it has one required thing inside of it, from iter. And from iter takes any type T as long as T implements into iterator where the item is A. Now this takes a little bit of thinking to kind of think through these types, and the reason that it's built this way is because this is the ultimately super flexible thing. This is quite complicated so that we have ultimate flexibility for our users. IntoIterator, again, is a way to take a type and turn it into an iterator, and of course its item is whatever the iterator will ultimately yield. So what we're saying is we want from iter to take any type T. It doesn't have to be an iterator. It just has to be able to be turned into an iterator through IntoIterator right here. And whatever that iterator will yield is whatever we're generic over in my from iterator here. And so when we go up to our usage here, my from iterator, that type A here is whatever our my iterator yields. And so ultimately, we will be able to turn our ourselves into, and this of course should be, do we actually implement? We never implemented a my IntoIterator, unfortunately. So this will be a little bit tricky. Again, you have to have all these types that know about each other and work well with each other, or all these traits, whatever. So I think we won't necessarily be able to do it right here, but we should be able to understand the kind of the layout of this method here. Any questions about this from anybody? So I'm going to change this real quick from IntoIterator, since we never implemented our own into my iterator. At least I didn't. Maybe I'm just losing my. No, we did not. Right? Okay, good. No, we never implemented that. And so I'm going to change this into, instead of being ultimately flexible and saying, give me anything as long as I can turn it into an iterator. Now we say, give me an iterator, or more concretely, my iterator. So once again, from iter takes a my iterator. We can, just to make it clear what we're talking about here, change that. It takes a my iterator right here, and produces self. Cool. So then in collect, what we can say is simply be from iter self. That's pretty straightforward. So this is the implementation of collect. It's not really magical. All it's saying is we have some generic type B. All we know about it is that it implements my from iterator. So we can produce a B as long as we have a my iterator. And it just calls that from iter function on it and says, hey, give me that B. I'll give you the iterator, you give me the B. And so now we can go down here and say this dot collect, and instead of this here, we'll say this is going to be new vec, and it's going to be a vec of strings. And we get a fairly straightforward error message. Let me run it in the console so you can see it printed out a little bit more nicely here. It's saying, hey, the trait bound vec of string is not implemented from iterator. So I don't know how to turn an iterator of strings into a vector. I don't know how to do that. And Chad, I just I think dipped on internet connection. Hopefully everybody's still there. Just let me know if the connection has lasted. Great. So really all we have to do is tell the code, how do you take an iterator of strings and turn it into a vec of strings? Okay, and that should be pretty straightforward. All we have to do is impl my from iterator of string for vec of string. And we implement from iter of any type t. Oops. So it takes any type t and produces self being a vec of strings. And I believe we can just write that. I don't think you have to write self there. Vec of strings. Just to be a little bit more clear what's going on. And we need this where our type t is a my iterator, where the item is a string. And I think it's complaining at us. Oh no, it's not. Good. Just saying we haven't finished our work here. So we'll use our old friend to do. Great. So real quick, we are implementing my from iterator of string for vec of string, where we say from iter takes any type t as long as that type t implements my iterator, with the item that it iterates being a string. And then, there's many different ways that we can implement this, but I think probably the most straightforward way is to just say, we've got a vector here, and we say while we keep getting an item from our iterator, which is my iter dot next, then we push onto our result. And we return back to the result. So again, how do we take my iterator and turn it into a vector? Well, we create a vector, we iterate, we call next on it over and over and over again as long as we get some. We push that item onto the vector and return the vector there. Pretty straightforward. And now this compiles. And we can say print line. We can prove that it's working by printing out our UVec it is. And there it is, 1, 2, 3, as a string. Okay, so I think we have a great question from chat. Real quick, let me go back up to the code. I believe, yes. So the question from chat was that this syntax confuses me as a Rust newbie. Totally fine. Again, this isn't really a newcomer stream, so apologies for those who are very new to it. It's definitely an intermediate stream, but this is great. Why couldn't you simply say my iterator t? So like this. My iterator string, sorry. Let me see if it gives us any kind of, probably doesn't give us any kind of good error message. No. So the reason that this doesn't work is this syntax with the braces here. What this is says, give me a generic parameter. Give me a parameter that is, that you want to generically deal with. We choose t, the name t here, because that's just convention. But we can call it basically anything, u or foo or whatever. We call it t just out of convention, some type t. And what we say here is we can do this in two places actually. We don't have to have this where clause here. We can say that t implements, so t is some type. You can think of the compiler basically as coming in at some point and saying, oh, here's a generic type t. I'm going to fill in wherever t is used with some concrete type. I'm going to paste in, and this is in C++, this is almost kind of exactly what it does. Rust works a little bit differently. But basically it goes in and says, you want to use some concrete type, let's say vec or, some other type, u32, whatever. And I'm going to paste in that type as long as that type satisfies this right here. So I will paste in your u32 as long as u32 implements the myIterator trait where the associated type is string. Now, does u32 do that? No, we have never implemented myIterator for u32, and we probably wouldn't because it doesn't really make sense, right? How do you iterate over a number? especially strings over a number. But for our my map, where we got back strings, then indeed, that satisfies this. So we will kind of come in and paste the my map type directly in wherever t is. Now, the question was, why can't we just write it like this, my iterator of string? I won't make a comment on why specifically why Rust did not choose the syntax, but how do we then say where we're using that type, right? So we need to say that it's actually my iter that is of type my iterator of string. So this syntax doesn't really make sense, right? You could imagine then a syntax like this. This syntax actually used to work, and it still does. It just gives you a warning that the correct version of this is now this, for reasons that we'll talk about in just a second. This is very different. This gets into the difference between, and again, this is a reason why Rust is a low-level language and not a high-level language. You have to worry about some of this extra stuff. The syntax we saw before was what's called static dispatch, where it literally at compile time creates new functions, new from iter functions for every type t where we use from iter with a new type. So we're using from iter with type, some concrete type my type and some other concrete my other type, and it will literally copy paste the function into your binary for each of those things. So you end up with different functions that work concretely with different types. In your binary, they're actually different functions. What this syntax right here says instead is that this is dynamic dispatch. What's happening is there's only one from iter function here. And what we do is we call through a vtable in order to access it. We don't know what type we're passing in here. And in fact, we have to pass it behind some sort of reference. We have to box it, or we can't just pass in a type because it doesn't know what type it is until runtime. It doesn't know what type it is. And so it needs to deal with it through a vtable. Now, if any of that makes sense, it doesn't make sense to you, that's fine. The idea of dynamic versus static dispatch is a whole nother topic that deserves a whole other stream. For now, basically, you can think of this syntax again as, I've lost the code. You can again think of this syntax as there's some type that will fill in later. And all we know about that type is that it implements the myIterator trait. So only functionality that we know that it can do is whatever is defined on myIterator. I hope that makes sense. Let me know if that started to make some sense in some ways, but not in others, and I can readdress it. Can you use the impl syntax? Yeah, you should be able to use. There's a different syntax that I usually don't use that is like this. And as this doesn't work for, because it has to match up here. I'm not sure if this will work, but in theory, these are kind of, these are equivalent to each other. This is, it's blowing up for some reason. Interesting. I'm not sure why. I'll leave that as an exercise to the reader, why exactly that's not working, but in theory, that's sort of moral equivalence to each other. It's newer syntax that is, yeah, sometimes equivalent to the generic syntax. So, and then chat is saying, no problem on the static versus dynamic. That's great. C++ programmer. So yeah, that should make sense. What strikes me as weird is that the type is constrained so narrowly. Yes, so the type is quite narrow. Like what chat is saying is it's this is a quite narrow scope. That's true, but in theory, there are infinite number of types that could implement this, right? In practice, there probably won't be, but I mean, there's nothing that says that you couldn't have a jillion different types that implement my iterator when the item is string. So, you know, just because the constraint is fairly narrow, in this case, in our program and in the world that we've built so far, there's only one type that implements my iterator where the item is string. But that doesn't mean that there won't be more in the future. And there could potentially be infinite number, as many as we could ever plan to write. All right. I think that's it. I hope that this was kind of as a whirlwind tour. We did something that you will never do in real practice, and that's implement your own iterator trait. There's already one in the standard library. Use it. But hopefully this gives you a kind of glimpse into how that iterator trait works in very fine detail, so that when you run into the iterator trait in practice for actually using it or needing to implement new types of iterators or new functions that work on iterators, it should hopefully make sense what's going on. Really, at the end of the day, it's just a next function, next method that's getting called over and over and over again. And there's a bunch of traits that kind of help you convert from types into iterators and iterators into types. But that's really what's going on. Any final questions before we end it for the day? Very informative. Thank you. I'm glad you found it informative. That's good. Sometimes I'm sitting here thinking, I don't know if anybody is understanding the words that are coming into my mouth, but I hope they are. And if you don't understand what I'm saying, it's not your fault. It's mine. Don't think that you are not capable of understanding what's going on. At the end of the day, it's not really that difficult if you can think through it. And it might take a while to get to that point, but it's definitely not impossible. Cool. Seems like we had some people who had fun today. Thank you very much for that. At the top of the screen, you can find my social information on Twitter, Ryan_Levick, YouTube. You can find this video on YouTube after we're done. I'll post it. I'm on GitHub as well. Happy to talk about any and everything Rust related on those channels. And if you have any ideas for the stream, I'm just going to open up Discord again and remind you about the Rustaceans Station channel, where we also we can talk about this after the stream. I'll be around for a tiny bit of time afterwards. We can talk about it there. Please let me know. Please like and subscribe on all these things so that I know that people enjoy what I'm doing and will continue to do it. I have a lot of fun working on this and doing this with all of you. So it really means a lot just hearing from anybody and everybody about how they find the stream. So with that said, I hope everybody... when will the next stream be? I'm trying my best to stay on every Friday at 4:30 p.m., 16:30 Central European Standard Time. I'm in Berlin. That is 10:30 a.m. Eastern time in the US. You can do the math hopefully from there. And I usually post on Twitter when I'm doing it, so you can follow me there. If that time does not work for you, let me know as well, and please let me know what you would like to learn about next. Also, that really helps. So, with that being said, Chad will stick around for a little bit longer. Thank you very much. Have a good weekend, and hope to see you next time. Bye bye.